Welcome to today's webinar. The topic today is form finding and calculation of pneumatic membrane structures in RFEM 6. My name is Andreas Hörold. I'm responsible for marketing and public relations in the Dlubal Software company. For instance, the website, the German and English webinars, newsletters, and so on. I will be the moderator today, and I will answer your questions together with Jürgen Teilmann, and Stefan Hoffmann will be the presenter, but my two colleagues can introduce themselves.
Thank you, Andreas. So my name is Stefan Hoffmann, and I'm working at Dlubal for 3 years already now. And I'm mainly working in the customer support by answering mails and phone calls. But I'm also involved in the development of our wind simulation and form finding or cutting patterns. And that's the reason why I want to present the webinar today for you.
Yes, and my name is Jürgen Teilmann. I also work in the customer support of Dlubal Software. I've been in the company for about 1.5 years now, and I also do some online trainings for our customers, and this is the reason why I will be answering your questions today. Now back to Andreas.
Okay, thank you for your introduction. Then we can switch off our webcams so that the attendees can see the full screen. Some words how you can ask questions for the attendees who participate the first time. You can show or hide the control panel on the right side of your screen with that arrow here, and then enter your question here, and we will answer you. If you don't get an answer during the webinar because there are too many, you will get an email afterwards. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. Before I hand over the screen to Stefan, I would like to invite you to our booth on the Bau in Munich. Yeah, just book your live demo and you will get your free ticket with that link here, or you can scan the QR code. Okay, that's all from my side. I hand over the screen to Stefan, just a moment. Okay, Stefan, it's your turn.
Thank you. So I think I already took over the screen, and you should now see the PowerPoint presentation with the first slide I want to present you. So this is the content of today's webinar. So the main effort is, of course, to present you the form finding add-on of RFEM 6. And thus, I will introduce you with an overview of some new features we are working about or which are already implemented since the last webinars. We will model 2 pneumatical systems. We will hand it over to our digital wind tunnel, so our wind simulation. And we will later on do a design of the supporting structure. And last but not least, I will show you some prospect, what are upcoming features, what is planned for development, and later on Andreas will conclude. So let's start with the first slide. So this is the overview of the new features which were implemented. Of course, not a full list, but some parts which I want to present you. The first 2 are still not released, so you cannot test it currently, but I can already show you what is planned, what is implemented, and what is the topic about. So first of all, it is a surface load of the load type ZAG. So you can define some movement of a cushion or of a membrane into a certain direction in order to find the shape. The next one is the ponding load. So this means it's some rain falling on your membrane, and if it's already bent in some direction, it is an iterative calculation where the load will increase until some equilibrium is found. You can imagine that by having a tent which is not fully stressed and it will rain on it, and then the membrane, which is quite weak, will bend a lot. The next feature, which is already implemented, is the difference results. So whenever you use your form finding shape, which is a bit different to RFEM 5, since it's not a complete initial state, in RFEM 6, you are now able to define multiple initial states. So it's like you create one form finding shape, you can put the snow on it, you can create a second form finding shape where you put some other load combination on it. And if you do that by using an initial state, you can check for the difference results. to see what is the additional load bringing to you. And then you can, of course, also check the final results as a summary of the initial state and the loading. And last but not least, due to the fact that we are now using forces as definition of form finding forces, it's not an additional option of a member now anymore or of a surface. I will later on show it to you. You are now also able to use set of member loads, which is quite useful if you have to split your cables to single members. You can define, as you are used to, a set of members and also load them with a form finding load. So let me shortly close the presentation and I will show you an eye catcher model at start. You can as well find the model usually at the webinar page in order to check it. So this is a simple overview. I want to show you about some different cushion shapes I have found in a manual. So you can see that there are some rectangular, some multi-corner shapes, or also some circle shapes or some elliptical shapes. And you are, of course, able to define cushions in RFEM 6, maybe not as you are used to with a so-called beige-plane surface type, but all you need to do is to create a solid, and I will quickly delete the mesh in order to show you how you can, in RFEM 6, create a cushion. I'd like to show it at the rectangular example. So all I did is I have created 2 times 4 surfaces, and I have moved a middle node at a certain distance. In our example, I moved it roughly 250 millimeters into one direction. So it, for your understanding, does not matter how far you move the node. It's just a modeling issue because you set the boundary conditions for the form finding process in order to find the shape of the cushion. So it just has to be at least 1 millimeter, but in order to be able to model it a bit better from viewing the model, you can also increase it. And later on, with regards to the boundary conditions, like the inner pressure of the solid, in our case 300 Pascal, and the isotropic form finding pre-stress of our surfaces, it will find a shape. So as told, if you want to use the form finding add-on, you will have to activate it in the add-ons. And then it is not an option, as already explained, that you have to have some edit button of the surface now in order to define a form finding load. Now you can find the form finding load as a usual surface load. So this is now your task. Usually, if you do a normal static analysis, you use the force load type. But now you can see that there's also a category of type form finding. And then you will, of course, be offered, as used in RFEM 5, for different calculation methods, also different form finding definitions. And then you can enter your form finding load. I did 1 kilonewton per meter as our isotropic form finding pre-stress for the surfaces. The same goes for the solid loads. So now it's not a setting of a solid, but it's a load type. So the load type is not form finding. For a solid load, it's a normal load type of gas. And then you can define a certain gas behavior. So like resulting overpressure or some other type. You can see in the small picture some explanation of it. Or if you hit F1 and go to the form finding manual, you can also see some explanation in there. So you can find, for example, a chapter with the form finding loads. And if you're curious what the solid loads are about, you can just quickly check it also in the manual. Okay, so last but not least, there would be, of course, some member loads. I do not have any member currently defined, but I can show it then later on in the member set loads, what the form finding loads can be or how they can be defined. So if you introduced all the, let's call them boundary conditions, you can apply them in a separate load case. So since I will not load these cushions in our quick example model with some other loads, I have only defined one load case of the action category pre-stress. And since we are using the form finding, we have, of course, to do a large deformation analysis. And if you want to adjust some settings of the form finding, like the number of iterations or the speed of convergence, this can be done in the static analysis settings. but we do not want to do it at the moment. If you did so, just once again to recap the eye catcher, we run the iteration. It will do then a third order calculation. It will move according to my set forces all the nodes to the correct position or to the expected position, and then you will receive a result. As you're used to, you can of course display the contour lines. This means this is the distance from the global z-axis with the 0 point into the global z-axis direction, because it's the easiest way to evaluate the deformation. And you can see that our cushions are loaded equally with isotropic pre-stress. They have different dimensions. This means that, of course, due to the equilibrium, they will have a certain different distance. If you will check for the displacement, take care that you always use a display vector of 1, because otherwise the results might be a bit misleading, and that the shown deformation of 1 meter approximately is the deformation with regards to the standard model mesh. So you have to add 250 millimeters, for example, at the middle node in order to achieve the deformation which is shown in here. Okay, so this is most likely, or this was most likely the eye catcher, and some recap of how the form finding add-on can be used. And now I will switch into the pre-release version. So this model is not introduced on the website, but it is available for us. And I will show you the first model, what I already created. And this is the one which is about the ZEC definition. So mainly this is a 6 or a shape with 8 corners. And it is meant to be loaded by inner pressure. And usually in order to determine the ZEC or the deformation of the cushion, you will have to enter a pre-stress with the current options you have. So usually if you expect a certain deformation of 2 meters and 5 centimeters. In our example for the shape, it was calculated that you need to pre-stress it isotropic with 2.75 kilonewton per meter if you have an inner pressure of 300 Pascal. This is sometimes quite hard to evaluate how high the stress will be. You can of course test it, iterate it, and try to find the shape you want to achieve. But now we introduced or are going to introduce in an upcoming version. I cannot fully determine when it will be there, but it should be there soon. That you can define a form finding definition now, not only based on force or stresses, but also based on the ZEC definition. You can see a bit in the preview how this will then be meant. You enter a ratio. So this is now not a value of pre-stress, but a ratio. So if you want to have an isotropic pre-stress, you enter just 1 and 1 into the normal x and y axis of the surface. And then you can define a ZEC, which is then, of course, the highest deflection of a surface, what I entered now as 2 meters and 5. And this is then related to 3 points what you can enter. The base is of course the base of the surface. So if I quickly show it in the snipping tool, the base is of course if you have a base and then you will have some bent membrane. This will then of course be the base value from there going to top. And the next one would be you are able to define a coordinate system. So this means currently the coordinate system, if you do not define something, is the base, but you can also move the coordinate system top or bottom, and then the deformation would be, of course, measured from this point or to this point. So you're also able to set a certain coordinate system in order to have a certain ZEC defined to that coordinate system. It's also possible for an angled cushion, or also for angled cushions. So I will just quickly run the form finding calculation, and then you can see that we will get, of course, the results we are expecting if we enter the ZEC or the isotropic pre-stress. So you can always check the convergence diagram. It's not linear because it's of course a nonlinear calculation, third order. And then we will get the results. I will just quickly only display those both because this one has a certain different ZAG. So if you can see that you can achieve both the same deformations of approximately 2 meters and 5 if you enter isotropic pre-stress of 2.75 kilonewton per meter, or if you define it by the base of a ZAG of 2 meter and 5. So we can compare now also the internal forces, which should be in a similar region. Of course, this looks quite smooth. I have now displayed the results moving as constant on mesh elements because I prefer it to be displayed like this. But you can see that our surface ZAG definition will also achieve a result which is approximately 2.72, and here we define 2.75, and also into the Y direction. It is also in the region of this definition. So we match the form by just entering the ZAG in this example. It also works for this angled cushion if you define a coordinate system. So you can also define, of course, coordinate systems in the program by edit them or entering them in here. And you can also activate them if you go into the navigator and set it active. And then you can see that for the angled cushion, I have defined also an angled coordinate system. You can, of course, also use the base in order to have the cushion being bent. And to achieve the 2 meter and 5, 90 degrees or into the normal axis of the surface. What I did in my last example is that I adjusted the coordinate system. And let me quickly display the shape. And now we have a 1 meter higher shape of the cushion. And what I now did is the thing that I defined a coordinate system for the top one, which is moved 1 meter bottom, 1 meter higher, sorry. So you will have, as shown, a 1 meter higher line. Thus, the 2 meter 5 will be meant from the line, and the base of the cushion is on the bottom. So the total value will be 2 meter and 5 plus 1 meter, which is the distance, and over here. So we will achieve then 3 meter and 5. And since it can bend a bit higher, the inner pre-stress will of course be as expected lower than the 2.75. So this is a tool you can hopefully use in an upcoming version. Let me close this and let's go to the next example, the ponding load, which is also yet only available in the pre-release mode. So I will open my created file. It's a simple 4-node supported membrane where I have cables at the edge, and I have defined a isotropic pre-stress with the dead load in order to bend the membrane a bit. What we will need for this ponding load is our 2 points. So you can have most likely something like a shape what is having rectangular walls, where you will receive most likely also a volume which can be filled, or you will have a pre-stressed mesh according to a theory third order. As you can see, we have now a bit of bending downwards to the Z direction, and then you can apply a ponding load. If I double click on it, it is from load type ponding. Once again, to remind you, it's not yet available in the normal customer version, so you will not find it currently. But it will allow you to define some rain or ponding load. So you can either use that you will fill your full shape until an equilibrium is found, or you can define the amount of precipitation, so meaning that it will rain 10 millimeter per square meter in order to have some static standard requirements being fulfilled, or in order to decide if it will be available, that it will stand if it's raining that high, or if you have to have some improvements being done. So in our first example, we define for this 10 square meters precipitation of 10 millimeter. We will let the iterative calculation run, and it will give us some certain deformation, and it will give us also roughly 10 kilonewton, what we would expect. Since it is raining, you will have some bend shape, and then you could calculate the volume according to the amount of precipitation. You can, of course, also increase it. So if we 5 times have it, we can also let it run. And it should also be later on possible to use it with a snow, but this is all part of a later development. So this is meant in order to fulfill some design checks you may need because some structures already collapsed due to high rain amount onto bent membranes. So we will now close the pre-release mode and I will step back into the normal mode. Let me quickly close this and I will go to the next part of the presentation. So the difference results. So this is already in the main program. I have created a structure of 2 membranes. So quite an easy 4-point supported structure with cables at the edges, a normal isotropic prestress, what I will give on it, and I will quickly run the initial state. So this is, as you're most likely used to, the normal form finding calculation also done in RFEM 5. But this is then being done in the main program, of course, and I will receive a shape. I will use an isotropic 1 kilonewton per meter in this shape and 10 in this shape. So you can see that, of course, the inner forces, let me quickly go to the inner forces of the surface, they will differ. So you will reach 1 in here and 10 in here, but the shape should be the same since the ratio and the external loads is the same. So the deformation of the membrane due to the same ratio of the forces is equal. We will now apply a snow load into the projected direction of all surfaces, and we will combine them in a load combination. And keep in mind that due to the fact that our initial condition is always to be needed as our form finding condition, of course, now in RFEM 6, you will have to consider the initial state from it, where we take over the final state. So everything, most likely deformation and strains are taken over. We can hit calculate. It should usually run the initial state, but we already have these results. So it's now only calculating the combination. And we can see that, of course, we will receive some results and a new tab will open and the result navigator, where you can now differ between the final results and the differences to the initial state. For this, I have already created 3 windows and I will tile them vertically, horizontally. Let me quickly reopen them. And on the top one, I will present the initial state I have chosen. So let me quickly display the inner forces of the surfaces and also the internal forces of the cables around it. And then you can compare the results with the differences to the initial state if you want to compare them. So don't be afraid that now a membrane can show positive, or let's say compressive strength forces to you. It's over. It's not shown. Now you can see in here. So we would receive some minus values, but we will never expect for membranes. But it's of course difference of the result. So it will then has to be sum up, and you can as well, of course, also display then the final results, which is then a summary, of course, of the difference and the initial state. So if we would display in here also the inner force as a quick example, 47, 46 will sum up to 93, of course. So this is a tool that you will not have to do some hand calculation in order to differ what the external loading may do to your membrane. You can quickly evaluate it already in a combination. So let's close this example, and I will open the last example for the first part. So this is now the set of member loads. I have opened this. So it may be due to the type of structure you need to model that you will have to split your cables. So this is a 10-meter cable into different parts. Depending, maybe you do have a cable net or something like this. And if you would do so, and you would define a normal geometrical load, so we will recap as told, we can edit member loads as a load type of form finding. And if we choose now the definition type of geometric with a normal member sec of 0.5 meter in the middle of the member, we will never get a shape what we will get if we will have a full cable, since it is then always based on the local deformation of the member. So the results will not make any sense at all. For our normal cable, we will have our 0.5 meter. And also if we define a member set and a member set load, which can be defined on over here. So you will have to ignore the first buttons if you use the member set loads. You can see that there are various options also for surface sets and also for solid sets that you can set some set loads. So this will be, of course, then the expected deformation. And the same goes if you would not define a 0.5 meter, but 5%, which is then, of course, also 0.5 meter. You can now do it if you have a split cable chain to create a surface set by just marking all members, of course, and create a member set. And then you can also apply member set loads in the form finding process, which was not able in RFEM 5 because it was a setting for a member and it was not possible to set it for a member set. Okay, so let's close it. And then we already managed to finalize the first part of the presentation. And I will now switch to the reference example. It is a screenshot out of the book of construction with cables and membranes from Mr. Wagner. So it's of course German and not translated, but I will translate the main facts for you. So we will now model, as maybe 4 or 5 years ago, I think we did show it for RFEM discussion, 4 times 12 meters cushion. And it is loaded by 300 Pascal in the middle, and also with a snow load and a wind suction. And we apply enough forces in the way that we will reach a sag of 0.4 meters. And then we will apply some loads in order to verify it also with the results they achieved in the program. So we will start by modeling this now. So you, of course, first have to choose for a name. I always tend to write the date at first, and I will give it a name. You can, of course, also adjust some project folder. We need, of course, 3D, and we will need, of course, solids because it's a 3D structure. And then we will, of course, need our form finding add-on. So we will activate it, and all the other stuff is not yet necessary or needed for our definition of the model. So we will just skip it and hit OK. You can also load a template if you want to, but now we have our blank file. So now it depends, of course, on how you would like to model a model. You can start by defining all the properties you need, or you will start by the geometry and define everything you need later on. It's up to you. So I will start with a new line, and as told, it is 4 times 12 meters. So I just will use the normal grid, which is in the background, and draw my rectangle for the cushion. So this is at the plane of global z-axis is 0. And then we will have somehow to create a solid out of it. So we can now not define a baseline surface, maybe, as you are used in a geometry type of a surface. We can use now NURB surfaces or quadrangle. This is up to you. If you want to use the NURBS surface, you will also have to use NURBS lines in order to determine your shape. But from my point of view, a quite quick way is that you just think about where is the middle of your cushion in order to check for some pre-bent solid or pre-constructed solid in order to give it a pressure and also a pre-stress. So what I would now do is I would simply split the cushion into a half by introducing a line. I'm always used currently to just cut it, and then I will have my lines also being cut in over here. And then I will define a new quadrangle surface. Take care that the preset is NURBS, so you have to click the small arrow in order to be able to define a quadrangle surface. As you can see, it will start with the materials of my last file. So I already have a thickness type defined and a material defined, but let's quickly recap on how you could define a material for your membrane. In RFEM 5, we did not offer any materials because membranes are most likely up to their producers, and you will have a certain data sheet of their settings. So we have now introduced two types of membranes. You can use them if you go to the material type of fabric, and then there are some materials to select. So it's up to you if they match with the materials you need to use. Once you define it, you can, of course, double check for the material values which are introduced. So if I don't use user-defined, you can see that this type of fabric membrane has a certain different E-modulus into X and Y direction. This is the local direction of the surface. Thus, it is, of course, representing the strength of a normal membrane. You can also hit the material values tab in order to check for the tensile strength into the warp and the ref direction. So in our case, it's similar. Usually, we would now, most likely for this example, have to adjust it. So I have already defined it will be a user-defined material for orthotropic direction, linear elastic surfaces. And I have defined an isotropic behavior. So you could have, of course, also chosen isotropic. These values are up to the reference example out of the book I showed you. You can also check for the stiffness matrices, which are then converted in Newton per square millimeter in our example. And if you would like to do, you could, of course, also apply a stiffness modification. So this is everything we need. And then we usually need a thickness type. And if you define a fabric material, the thickness type will automatically be used for it with a thickness of 1 millimeter. Maybe you remember, if you already used RFEM5, we always tend to have the material properties being scaled by 1 meter. Now we decided, depending on the setting for the unit you have done in the program, to use now 1 millimeter. And this will then leave you with a quite quick comparison of your material properties to the given warp and weft strength, because it's quite simply then converted. But if you do not want to have to enter a 1 millimeter thickness, you may not use a fabric material type. You can then define your own material if you really want to and give it the correct thickness. But as told in our example, we will use a fabric material, so it's then being used by 1 millimeter. So we did it. The last thing is, if you would now hit OK, it will claim that the material is not supported for this surface because this is an orthotropic material and we have the stiffness type as being standard. We will now, of course, need to use a membrane, which can only carry tension forces, of course, and then the warning will not appear again. You can then define your quadrangle if you want to, but as I can see, I have forgotten to do one thing. Now we could, of course, define a planar quadrangle, which is not sufficient for our solid. So what I would now do is that I divide this line in one node, and then I will just quickly copy paste this or move this node with our tools we have. In our example, I will move it 250 millimeter. I always fail. It's meter, so minus 250 millimeter. So you can also enter a unit, and then you do not have to think about the conversion in here. So we have now put it to have a small movement into the global Z direction, and now we can define our top shape for the cushion. So once we use the thickness already defined, and we just hit our planes. So you can see the shape is not really looking smart. So you can double click on the quadrangle. If it is defined in a weird way, you can hit the graphical display, and we can now see that the corner nodes are automatically taken as 1, 5, 7, 6. For our shape, that does not make a lot of sense. So we would like 1, 5, 6, and 2. So we can quickly just choose a node in here, hit apply, and redefine our shape. If you want to see it a bit better, you can also have it filled, and you can see that the shape of the quadrangle is not really looking smart, but you can already see it if you have the dotted line. So in our case, we will just quickly rearrange it. You can also choose this button in order to choose for 4 nodes. It's similar to RFEM5. If you have more than 4 corner nodes, you will sometimes have to adjust the shape of the quadrangle, because this then also defines the FE mesh, and if it's too crappy, then it might be not a smart calculation for you. What I would now display is also the local axis system. So you can see it's a bit angled. So we can mark both surfaces and specify the axis. This is usually, or was usually, necessary in the past by defining it for orthotropic pre-stress, what we will also apply. So I just choose this line in order to have my x direction of the surfaces being parallel to this line. And then my y surface local axis will of course be 90 degrees. So I will now mark both and reverse the local system because I will have to have the z value being to top. All right, if we do so, we can mark our boundary lines, or you can mark everything and hit Shift and deselect these ones, and we will just simply apply a normal line support, which we will directly hide because I think it's a bit too high. You can also too wide. You can also hit the right click and smaller the line support, but since it's not mainly necessary for us, we can also hide it. What we can now do is we will just mark everything and then we will mirror it just with the normal definition, and we will use the XY plane in order to mirror it. I always forget to hit the copy button. As you can see, it's always happening to me because we want, of course, to create a copy. And then we can double check once again, of course, on what the shape of our membranes will be on the top one, and double check the corner node definition if we want to. 1526 sounds quite good. 1526. Okay. And then we might double check, of course, the axis system if it is also to line number 2. It is. So I'm just weird, but the coordinate system should match. You can also as well reverse it if you want to, of both surfaces, and then we will have most likely our two shapes we need for our cushion. And the last thing is that we need to create a new solid, of course. It has to be a solid gas type of solid type of gas. The material has to be a gas material, so we will define a new material where we will go into the material type of gas, and we will just use dry air. Say okay. And then you will have to define a gas solid, which is the initial state for the gas. So we will use in our example just a normal definition of 1 bar and 23 degrees of Celsius. And then you will have, last but not least, to assign the boundary conditions. Say okay. And then our gas solid is defined. I will now switch off the local axis. And then we have, of course, our cushion being defined. We will then have to create the first load case. It does not have to be the initial state, but I call it initial state, where I will define my loads for the pre-stress. So let me quickly have a look how they did it. So they defined a surface load. You can also now define surface sets if you want to, but they have a form finding surface load defined that it is, I think, 0.5 into one direction and 1.56 into the small direction. So 0.5, 1.56. And they also defined a gas load of 300 Pascal resulting overpressure. So we will do it. It's already assigned to surface solid number 1 because there's only one solid. And this would be everything for our initial state. Let's check if our model is working. It's always one thing I would propose to you before starting entering some other data. And we would expect something about 400 millimeter of deflection. This depends, of course, on the FE mesh. The finer the FE mesh, the better, of course, the cushion will go to the expected deformation, but it's also some choice of calculation time. So we will leave it with the normal FE mesh settings we do have with the triangles for the quadrangle surfaces, and this is the shape you would expect according to the book. So it's about 0.4 meters or 387 millimeters. So now it is mentioned that they apply a snow load on it. So we will use a snow load for a normal system. You can also, of course, enter some definition in here. It's a wind suction, which is then defined. And Then you could, of course, think about entering the form finding data or the loads you want to have for snow and wind, because for the snow, we will have some open system where we will increase the pressure even more from 300 Pascal to 600 Pascal. Or you can also have a closed system where the pressure will not be increased, but it is thought that the cushion is closed, so it will stay at 300 Pascal. And we will also do it for the wind suction, where it will mainly stay at 300 Pascal, or it will be held by 300 Pascal. So this is most likely the difference between open and closed. So I will once as well create a new pre-stress load case where I name it 600 Pascal and one where I name it 300 Pascal in order to define my loads. So if you did so, you can also switch between the load cases and their definition. So for our 300 Pascal, we define now a resulting overpressure of 299.9 because we cannot enter the same amount because it's a resulting overpressure. We always need a small overpressure increment. So in our case, we define 299.9. We have a resulting overpressure now we want to achieve. So it already has 300. And if we define it by a resulting overpressure, we will now add 600 in here, of course, and define it to the solid. And the next one is snow and wind. So for the snow, you will have to pick your top surfaces and add a surface load there. It is mentioned as a normal force of 0.5 kilonewton per square meter into the projected area. So you can use the global Z system, of course. And then we will, of course, define the wind suction, which is also on the top surface. This is the reason why I reverted the coordinate system, so you can apply it locally as a force. And this was, let me quickly have a look, 0.78 kilonewton per square meter. So if we enter so, we have our forces. And the next thing is that we will have to define our load combinations. Currently, we have our design situations being done by the combination wizard. We will not use it for our example. So we will switch it off, the combination wizard, and we will define our own load cases. So this one would be the first load case, which is a comparison of snow open. So you would always have to consider, of course, your initial state if you want to choose it, and then assign, for example, if we want to have a resulting overpressure of 600 LC4, including snow. The next one is the closed one, so we will not increase the amount of pressure. The next one would be wind suction with the fixed inner pressure. And last but not least, it will be the wind suction without any increase. Okay, so I did quickly define them. We can now run our normal ULS, which is then the envelope, of course, and starting all the corresponding combinations. And let's only check for the snow load. So you can, of course, see once again the final results and the difference. And the thing is now that due to the fact that solids is displayed, you cannot really see the contour, but the top surface is bending a bit downwards. Let's check for the deformed shape. And the bottom surface is a bit higher. So this model is, of course, also available, so you can double check for the verification examples if we reach what we want to reach. You can also display the solid loads, for example, the volume of the cushion, and also the resulting overpressure, what we defined with 600 Pascal in our case. Okay, so this will conclude the first reference example we will also provide for you. And then it is up to the next part, so the modeling of our pneumatical example. Oops, sorry, Andreas. And I will go on. I will define a new model, but this time I will just open my model and already use the definitions of the materials and so on, because this is a basic stuff you can do in RFEM. So I just delayed my model, and then I have already my load cases and so on defined. Okay, so we will not start with a blank file. What I would now like to model is, did I close it already? Let me quickly go to it. It is some roof standing in Germany. So it's a 4-column roof. I always tend to say it looks like a mushroom a bit. So it's a quite symmetrical system with cushion in its place. And we will start by just drawing a first member. It's a normal section. So it's a normal SHS section. It is 4 meters high, and it is having a cantilever, or it's having a fixed support at the bottom. And this is all we need at the bottom. Then we will switch our plane at the top of the member, and then we can continue by drawing our members. You can also pick over the definitions if you want to from the current existing member. And we will have now a rectangle. So we will just use the normal grid in order to define it. And we will have one member in the middle. Already close the definition. Okay, so you can also drag and drop the node onto there if you did not hit it correctly. And now we will only move those corner nodes 2 meters higher. And this is most likely 1/4 of the shape of one mushroom. So the next thing is that we of course need to create once again a solid. So for this, I will once again draw a line into the middle of my elements. I will mark it and divide it into 2 lines. Then I will just simply mark my nodes, copy them with Ctrl-Z, Ctrl-V on the keyboard, 50 millimeters higher. You can see, depending on how high you move them, the easier it is to snap it. So I will now define a second line on the top. And this will leave you to be able now to define a quadrangle surface of the same thickness we used in over before with the same material. So we can now choose to pick the lines we need. Of course, I will now have ones to split this member because I want to have 4 separate membranes being defined. So now it's only picking some members. Could already think about what is the best sorting. So if you pick first the top and then the bottom, or pick first the bottom and then the top. But this is then up to you, of course. So all we need, of course, is to create the boundary shapes for our solid. So I think I have done all 4. You can also display it if you want to be filled. So the next thing is I mark every surface, I double click on them, and I specify my input X, because I always like to have my axis being localized to some certain line, what I know. So you can quickly then, of course, check for the local axis system always. If you rearrange them, maybe I did not hit these surfaces in here. 15. Does not like me today. Although it's okay, it just looked weird, but the x-axis is going into the line direction. Okay, I do not display them. And now I would go to the way that I mark my both top surfaces. You can see that it's quite hard if you only move the node a bit, but you can mark them, right click on them, and create a new surface set. So you can even give them a comment like being the top surfaces, and you can hit apply and create a new one and choose for the bottom ones and sell bottom, for example. So this is the way you could choose for surface sets. And then you can already define the solids. So I will define a new gas solid as gas, dry air, and the gas solid, and I will choose for my 4 boundary surfaces. I will do it again. Let's clear it because I already marked some surfaces before and hit it OK. So what I skipped by opening the model is, of course, that we will use a 3D model type and use now a form finding wind simulation add-on in order to create the wind loads on a not common shape. And we will also use the stress strain analysis, which is offering us a cross-section analysis. So we will not take care about stability problems of the steel members. We will only do a cross-section analysis of the steel members later on, as well as for our membranes. And we will use it for the German annex. You can see that in the initial file, I already defined some load cases. So I will have now some initial state. I will define a gas load. Once again, you can of course think about your own gas loads. We will quickly just choose 300 Pascal. You do not necessarily have to pick the solids. You can also define it by entering their number, which is a bit easier sometimes. Sometimes it's not easier, depends on what you want to do. We will quickly create a member set as well for these surfaces. So the top surfaces again, give them the comment, and one more for the bottom ones, because I want to define then surface set loads. Okay, and then I will define my surface set loads, where I can see, of course, my surface sets. Let's also give it a bottom comment. What will make it a bit easier for me, because I want to have a normal form finding load of 4 kilonewton per meter for the top surface sets. So I could now choose in the graphics, or I could just simply check my comment, what I did. So I define it for them as being 4, and I will define 2 for my other 2. And then I'm most likely done with the form finding definitions. You could then quickly already enter the snow load, which is in our example 0.5. Which is then, of course, also used to be a surface set load, 0.5 into the projection area. This will be assigned also only at the top, 1 and 3. And the wind loads will be later on, of course, being defined in the wind simulation or calculated. We will increase or define an overpressure for both gas solids. So you can mark them, new solid load, gas, 600 Pascal. Okay. So by doing this definition already for 1/4 of my structure, I can just simply mark it now and rotate it, create a copy of 3 steps, 90 degrees. Our Z point is 0, 0, 0, and I will of course use that it should be copied including loading. Say okay. And then it should be like it is defined in over here, that it has taken over all load case definitions, of course, and it will create a shape expecting to what I want to have. And we now simply go once into the 0 point because it's easier to check, and we will move copy it 10 meters into 1 X direction, copy it including loading, and just mark it once again because we have 4 of these mushrooms into 10 meters, copy it including loading. Okay, so if everything went well, what is usually not the case in a webinar, you can now hit F5 and start the calculation. So let's see if I did do something wrong or not. I will see some warnings. If we will see some warnings, we will just load my created file, which is having the same inputs. But it is starting into the calculation. So I will press my thumbs and check if it will run into equilibrium. So now this is the main form finding calculation without any external loading. You can of course also define for the initial state that you will have some loading. You can also have a form found shape and apply a dead load and use this combination as an initial state. So you're most likely now in RFEM 6 fully free, or more free than it was in RFEM 5, to use different shapes as a starting point or as a comparison point. And at least it did calculate. So I'm displaying currently the internal forces, should be 4 at the top and 2 at the bottom, looking good. And then it should have a solid gas pressure of 209 or 300 approximately, which is now 299. So everything looks good. So the next thing is you could now go and define your load combination. So in our case, I did just define sums. So the one-time snow load, an overpressure of 600 Pascal and the normal dead load, material dead load with the initial state from the form finding process. I have also the snow closed where we do not increase the inner pressure. and I have a wind load case where I will only apply the wind load onto the initial state. So this can be done by creating a load case of the analysis type wind simulation, and take care that you also consider the initial state from LC1, because this is then the shape which will be put into our digital wind tunnel. You can adjust also the wind profile and the analysis settings if you need so do so. I just kept the original ones, and I will not start the calculation of our wind because it will take approximately 7 minutes for this size of the file, even with the coarse mesh. I just opened wind by this button in order to display you that this will of course be given to our wind simulation tunnel, and it will for you, oh, it's now in German, sorry, well, but I will not show a lot of, but it will do of course the shrink mesh for you, and then it will do the wind load calculation depending on the inputs you do, and it will then retransfer the loads into our model. And then you can use the loads for this wind load case. Due to the fact that this will take some time, I did already calculate the model. So I will just open it with the final results. And then I can show you how the loads will then be shown. So all I did is I was just starting the wind calculation for this file already. And then you will get some loads. And for the wind load into X only, okay, so it did not take a while. Well, we should have to have results. I think we do have. Yeah, we do have, but not in the load case. But well, okay. So you can then, of course, also check for the results in the combination where we have then our wind loads being put on, and check also for the contour if you want to, which is not looking that easy since it's based to the local z-axis. That's why for this case, I would propose that you check the normal global definition with a normal deflection of 1. So once you have the results from the wind simulation, you would go into the design process. So this is then the stress strain analysis tool we offer. We will only do it for the stress analysis in our case, and for the times of or for the factor of time, I will only use the CU1 to be designed. In our case, I will not use every combination, and then you only have to click from left to right as you're most likely maybe used to it. We will only determine the surface set 1 because otherwise it will take half a minute longer. You can of course analyze every member and surface sets in order to get some results. The next thing is that for our surfaces, you will have to think about the surface configuration, which is of course being shown in the webinar if you have a look on the stress strain analysis, that you can analyze stresses and strains. We want to do only stresses in our example. And now it is usually based that you have a limit stress, which is given from the material. But as you maybe remember, for our material, we do not have a limit stress as it is for a normal steel. So a normal steel will of course have a yield strength as a stress-based, but our material values are per meter. So currently it's necessary to define your surface configuration, most likely similar to OFM 5, that you define the user-defined limit stress. And this is in our case 60 Newton per square millimeter without any reduction factor in our example. And then you can hit OK to calculate the design. It will run through, and since I've only designed one surface set, you can see that it's the only one being shown. And then you can of course evaluate your results in one full model in order to make the design process of course and have a full statistical documentation. So we will now display the stress ratios on members. It's of course not economical what we entered in here, but it is only meant to show you what can be done as a cross-section classification. And you can also display the stress ratios then for your surfaces, and you can also check them as well in the add-on if you want to do so. Okay, so this should conclude this part of this model, and I would just step back once into the PowerPoint presentation and hit, of course, the prospect in a full view mode, sorry. So To sum up my webinar for today, before I hand over, this is the prospect. Of course, we are working on releasing the 2 new features I showed to you, so the surface load of SEC and ponding load, as fast as we can. The surface load may be available quite soon. Ponding load is still a bit in development, but we are working on it. And I think most of you are already rating, of course, also on cutting patterns. So we are, of course, focusing on developing the add-on also for RFEM 6, that you are then as well able to determine the cutting patterns for your structures. Okay, so I will now hand over back to Andreas. Thanks for listening.
Okay, thank you, Stefan, for this nice presentation. I hand over or take over the screen now. Before I show you the website where you can find the recording and so on, I would like to invite you again for our booth visit on our booth on the Bau in Munich for all attendees who came later. You can get your free ticket if you book your live demo with that link or with the scanning of the QR code. If you don't have time to come to the Bau, you can book your free online appointment. You can book your free product presentation. If you have questions to different add-ons or to the programs of RFEM 6 and RSTAP 9, you can get an offer from our sales team. Just scan the QR code or click that link here. You can find all on our website, the PowerPoint slide and the recording here, dlubal.com, and under news and events, you can find the webinars. That's the webinar of the next week, construction stages. If you are interested in, then the week after next week, code formed steel sections, our FAQ webinar. And that's today's webinar. I click on it. In the next days, you will get an email with a link to that page here. Then you will find the recording here. The PowerPoint slides are already here. And also the models. Okay, that should be also all from my side. I thank you for your attention. Thanks again to Stefan for the nice presentation. Thanks to Jürgen for answering the questions. Maybe a last hint, when you leave the webinar, there is a small survey. It takes you only 1 minute, I think. You can score the webinar. Just note that the worst score is 1 and the best score is 5. You can leave wishes for future webinars, for example. But you can leave that empty or enter a sign such as minus or so on. Okay, I wish all a happy Easter. I hope we meet each other in a future webinar. Bye-bye.